All right, how's it going? Any questions? So midterm tomorrow, it's all about lists. Okay, so if you have list questions, this is a good time to ask. So your midterm is 5 problems, 5 pages, 5 programming pieces. Some of these will be a few lines of code. I'll say show some C code to do such and such. Some of them will be write a function to do such and such. Okay, it makes a big difference. I don't want you spending time saying number sign include standard io.h, integer main, car, star, blah, 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 right? If what I want is 3 lines of C code to, change a pointer in a linked list or something, right? So if you're not sure how much I'm asking for, ask, right, during the test. Because you want to spend your time wisely. Some of the questions are more challenging than others. So my usual suggestion is when you get the exam, skim through the 5 questions, okay, and decide which ones you're pretty sure you can do and whip those out, right? Decide which ones you're pretty sure you can do, but they're going to take longer, work on those next, and then when you're done, work on the ones that you don't know if you can actually finish or you have an idea how to start. But budget your time, okay? Each question is worth 20 points. So there's no reason to spend time on a problem that you might only get half done and then run out of time and you can't do the other 4 problems, okay? Do the ones that you feel confident about, get those points, and then move on to the ones that seem more challenging. But they're all about manipulating lists and pointers to nodes and things like that, or dealing with structures in general. Definitely list with pointers, no lists with arrays. And PA3 is probably good practice for this, right? The stuff you're doing in PA3 is getting a little deeper into using lists, right? So thinking about what we've been talking about for PA3 is probably good practice also. But go through your code and make sure you understand, how you're doing add and delete and things like that. Think about drawing pictures and writing code corresponding to different operations. That's all good practice too. I think it'll be a good exam, but we never know till it's done. But I don't think it will disturb you too much. All right, well, let's talk about stacks. So we started with the basic idea, sort of intuitive view of a stack, which is you're doing some task and something comes along and you have to suspend what you're doing and go do something else. Somehow we need to remember where we were before we go somewhere else so that we can return to where we were. Okay, a stack is a nice way to do that. So you're doing your homework, and while you're doing the homework you decide you're hungry and so you want to get some lunch. And while you're on the way to get lunch you realize you don't have any money, so you go to the ATM. And then when you're done with the ATM, you resume your process of going to lunch and you realize that you're running out of gas, so you have to stop and get gas. And when you're done getting gas, you return to the task of getting your lunch. And when you're finished getting your lunch, you return to the task of doing your homework. And when you finish your homework, you go back to whatever you were doing before you started doing your homework. Okay? So this has a structure that we call last in, first out. The last thing that we put on our stack is the first thing we take out of our stack. Okay, if the last thing we remembered was we're getting gas, then when we're done, we remove that from the stack. And the previous thing we had put on the stack will be the next thing that we get out. And so there's some terminology. We can say push some piece of data, and this means add data to the stack. Remember this piece of data. We can say pop, and maybe that's a function that returns a piece of data, and this says remove last pushed thing and return that to the caller of this function. So you say push a piece of data, it saves it on the stack. When you say pop, it finds the last piece of data that was pushed and it returns it to you. And it removes it from the stack. So that the next time you say pop, you'll get the previous thing that was pushed. And those are really our two main interactions with stacks, push and pop, push and pop. Push, 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 pop, pop, push, pop, pop. Okay? Every time you push, eventually you're going to do a corresponding pop, but they don't necessarily go one right after the other. So we push doing homework, we push get lunch, we push go to the ATM, we pop that, we push get gas, we pop that, we pop lunch, we pop homework. So those are the main two functions that we need, but there's other functions that we can find useful. For example, initialize, which most computers we might have to do some sort of initialization to create an empty stack to start with, just like we initialize a linked list or a hash. So we could say initialize a stack. And if you push things on the stack, when you pop, you get the things that you pushed, right? If there's nothing on the stack and you say pop, that's an error condition. Because pop says, give me the last thing that was pushed. Well, if you never pushed anything on the stack, you can't pop. Or if you've already popped off everything that you've pushed, you can't pop. So we have a condition called stack underflow, which is trying to pop from an empty stack. The other possibility, you're pushing things on the stack, you're asking it to remember. Eventually I'm going to run out of paper on which to write the things that I'm trying to remember. Or I'm going to run out of memory in the computer where I'm trying to save the things that I'm trying to save. So we can get another condition called a stack overflow. And that happens when you try to push to a stack that's full. In other words, a stack that cannot hold anything else for whatever reason. So the example I like to go back to sometimes, this is how I learned stacks, was you go to a Chinese restaurant, you go up to the buffet, and there's this big stack of plates, right? And it's sitting in a cart, and this cart is kind of magical because it looks like this. There's a little spring-loaded platform, and your plates are sitting on top of that. And there's always one plate just slightly above the top that you can easily pick up. And once you pick that up, you remove it from the stack, all of these move up one. The spring pushes them up, and now there's a new plate on the top of the stack. And you can pop another one from the stack, and another, and another, and eventually you've popped all of these plates off, and all that's sitting at the top is just this bare metal plunger, right? The stack is empty. If you try to pop, you get a stack underflow because you're grabbing the spring-loaded platform. There's no plate there to take. But there's some plates here. People are taking them. They're moving up, right? The dishwasher comes out from the kitchen with a big pile of plates, puts the plates onto here, and what happens? All of these plates push down, and these new plates appear on the top. The last plate that the dishwasher puts on top, that's the first one that somebody's going to take off. Okay, that's this last in, first out. So the last plate that goes on top, that's the first one somebody will remove. And then someone removes the next one and the next one, and off someone brings out 5 new plates and puts them on here. This top plate goes down 5 levels. You have 5 new plates on top. Those 5 plates have to get taken before this one comes out. Okay. So this is also a first in, last out. The very first plate that got put on here, which is this one down here on the bottom, that's not going to get taken until all the plates above it get taken. It's going to be the last thing out of the stack. Okay, this is not the way to save yogurt in your refrigerator. You buy yogurt and you push everything back, and you take yogurt and you pull everything forward, and you get new yogurt and you push everything back. That poor yogurt in the back from 1973 is never going to come out until you've taken all the yogurts in front of it. Right? That's a stack-based system. It would be like really supreme yogurt, like maximally aged. So we'll talk about queues after this, and a queue is what we would want to use in that case. But a stack, right, last in, first out. All right, so I'll come back to that model sometimes. So an overflow happens when you have put so many plates on here that spring is compressed all the way down. You put one more plate on top and it falls off the top, right? You can't put any more plates on here. The stack is full. That's an overflow. The other thing to note about stacks, yeah?
So could you say that the linked list that we're creating in PHP is kind of like a stack because we're only adding to the beginning of the linked list?
Yep, that's exactly how we implement a stack with a linked list. Yeah, perfect. So the other thing to note about stacks, you come up to the buffet and you're ready to get your food, and the top plate is like totally wet, right? You don't want that one. You want the plate below it, right? Well, you cannot get to the plate below it unless you remove that first thing from the stack. We always access stacks from the top of the stack. And if you want something that doesn't happen to be at the stack, you got to pull everything else off that's in front of it until you get to that thing. And then maybe, you put those other things back on the stack, or you hand it to the person behind you or something. But fundamentally, we always access from the top. And we can't usually, even though we can, we don't think of it as being able to access things that aren't at the top. So why do we talk about stacks in computer science? Because they're used all the time inside computers. And the main way that we see them is with call and return. So in C, we don't say call, we just type the name of a function, and it means execute that function, and when you're done, come back to where you were. In assembly language, you usually use the word call, right? So if you've done 270, call and return. And how does this work? Here's your main program. So you do something, do something, do something, and then you call function 1. And function 1 does some stuff and calls function 2, and function 2 does some stuff and says return. And maybe function 2 does some stuff and eventually it says call function 3, and function 3 does some stuff and says return, and function 1 does some stuff and says return. And main does some stuff and returns, and maybe main also calls function 3 and does some stuff, and eventually our main program returns. So let me label these locations. Okay, our main program starts executing. We say call function 1. We want to go off to here. We want to start executing this code, and when we say return, we want to come back to location A and continue with the next piece of our program, right? the problem that we talk about in 270, if we just save A somewhere in a variable called return address, right? Function 1 is executing, it says let's call function 2. We have to save C as a return address. If we just say return address equals C, we've lost that return address A. So when we call a function, we need to save the return location, but we also need to remember all the return locations that we're currently saving. So we'll use a stack. And the first time we say call function 1, we'll save its return address on the stack. This means that if you say return, you should come back to location A, continue here. Function 1 is executing, we see a call statement, we push the return address on the stack. So there's our C. We come down to function 2, it says return. Where do we return? We return to C, so we pop that off the stack, we come back here. Come along, call function 3, we'll save the return address of D. Function 3 executes. When that says return, we pop the stack to see where to go back to location D, that's right here. Now function 1 executes a return statement. How do we know where to go? See what's on the top of the stack, that's an A, come back there, and now we start executing here. And then if we call function 3 from here, we'll save the return address. Start executing function 3 and say return, right? And this is why we're doing all of this, because previously when we returned from function 3, we wanted to come back here. Now when we return from function 3, we want to come back there, right? If this was a function we were only using one place, we could just say go to function 3, and then at the end we could say go to here, right? But we want to return dependent to a location that depends on where we called it, so we use a stack. Okay, what happens when we hit this return? We try to pop something off the stack's empty, right? Except it's not. There's a whole bunch of other stuff on the stack that was put there before our main program started executing. And when we hit the return program that we wrote in our main program, we actually returned to something that called main. So there's lots of things on the stack. Poor CPU is dying. Come on. So here's a bit of an evil function. Alright, so here's a function called sub. What does it do? It calls itself sub. Right? And every time it does that, it has to save a return address on the stack. So each time that sub calls itself right here, it's going to push the return address, right, the address of this next instruction on the stack, and that's going to take space. And eventually this will blow up. So I've got a global set to 0. I'm going to increment that every time that I call sub, and I'm going to print out the value of global and see how many times it calls itself before it blows up. And it'll go about 175,000 times, and then we run out of stack space.
Is that limited by your hardware or by the operating system saying that's too many?
I think it's a combination, right? The operating system is helping figure out the stack size, I believe. Depends on your operating system, but it's also a function of how much memory you have. And, you know, this ran 174,577 times. This time it was 563 times. So it's not always the same situation because the memory situation on this computer is changing all the time. There's 100-some tasks running. But if we run this, and we change to an assembly layout, right? Well, let me do this. Let me get rid of the print statement. So if you say layout ASM, you can see your assembly language corresponding to your program. And if you say step I, it will step one instruction at a time. So it's about to do a move instruction. If we say step I, it'll do the next move instruction. Now it's about to do a call. This is the call to sub. Sub is a program that sits at location bunch of 5s 4610, and it's going to make that call. And 4610 is right here. Right, so it jumps down to location 4610. But the return address, which is probably the address of one of these instructions, has been saved on a stack. And I can step through this and eventually get down to another call to 4610. And that'll jump back there, but it's also saved the return address somewhere. So this is the location in memory. This is close to the location in memory where it's saving these return addresses. And if I go down to the call, there's another location. So let's just right, so what do I find at this location? 5555463B. That's the address of the instruction after the call. That's the return address. So the stack on this processor is just another location in memory. Series of locations in memory. And each time you push something, the thing you're pushing, the return address in this case, gets saved somewhere else in the memory of the computer. Right, so we'll look at how we implement that and how this is actually happening and what this RSP is. All right. So we talked about push and pop. And maybe we want some kind of initialization to create an empty stack. And maybe we want something which says, is the stack empty? So that we know if there's anything there to pop. And maybe we want something which says, is the stack full? So we know if it's safe to push. Mm-hmm.
So right now this is all pseudocode, not built-in code?
Yeah, this is all pseudocode. We're about to switch to code.
Okay.
But thinking of this as pseudocode, right, this is a fairly abstract notion, right? We have something that pushes data, something that pops data, something that tells us if the stack is empty. This is our view of a stack as an abstract data type. Okay, we always want to start by thinking of structures abstractly. A linked list is a thing you can traverse, you can add something to, you can search for something, you can delete something, you can initialize it, you can find its length, right? That description says nothing about nulls, nothing about node arrow next, nothing about list bracket index dot data, right? It's an abstract definition of a linked list. Well, this is an abstract view of a stack. It's a structure into which we can push things We can pop the last thing pushed, we can initialize it, we can tell if it's empty, we can tell if it's full. And as a user of a stack, that's what a stack is to us. It's a set of functions that we can use to interact with it. But the way that's implemented can cover a lot of different options. But if I want to use a stack, if I want to push some things on the stack and return some things pop some things from the stack, I don't care how it's implemented. Now on a PIC processor, this is implemented in hardware. There's a push instruction, there's a pop instruction, there's a special function register called top of stack, and there's locations in the silicon, there's transistors that make flip-flops, that make registers that are the places where the stack exists. It's physical stuff in the chip. On this processor, my laptop, the stack is just a bunch of locations in memory. 7FF with a bunch of Fs and then a 4BE6 or whatever we see. In some implementations, a stack can be a linked list. So we can implement these structures lots of different ways. Abstractly, we look at it like that. But let's look at implementation possibilities. So, if we think of the buffet version of a stack, and instead of a spring-loaded cylinder, we think of an array. Now let's just think of an array that holds 10 integers, so it's a stack of integers. And if we think of this as the top of the stack, then when we want to push something onto the top of the stack, we would just store it at location 0. Okay, in that physical model of the plates moving up and down, if we now push a 20, what should happen? This 10 should move down to here, and the 20 should go up there. This is always the top of the stack. So at this point, if I pop, I'm going to pop off the 20. That's correct. And the 10 will move up, and then if I pop again, I'll get the 10. And so if I want to push a -5, right, this would become a 10, this would become a 20, this would become a -5. So that mimics our physical model of a stack, things moving up and down. The top of the stack is always at the top. What's the problem with this implementation, though?
It's a lot of processing.
Yeah, it's grossly inefficient. If we had 1,000 things on our stack when we want to push, we've got to move 1,000 things down in the array to make space for the new thing. It's inefficient and it's not necessary. The only reason we have to do that is because we're insisting the top of the stack is always sitting there at location 0. So if we allow the top of the stack to move, we can keep all our data stationary in the array. So we can do an implementation like this instead. Here's our stack. Here's the elements. And we'll start off with the top of the stack right here. We'll push a 10. So we'll put a 10 there, but then we'll just change our top of stack to be right here. So when we say push 20, we'll put the 20 where the top of the stack is, and we'll change the top of the stack again. And now we push a -5. We'll write a -5 at the top of the stack, and we'll change top of stack again. Now if I want to pop, what do? I back up top of stack and I read what was at that location. So when I say pop, I will decrease top of stack to have it point here, and I'll return that value. Now if I say push, I'm going to push right into this location on top of the -5. If I say pop, I'll grab the 20. So the last thing we push comes right before the top of stack, that's the first thing we're going to pop. So we've got our LIFO. All right, so this is not too bad to write code for. So we're going to have a variable called SP. That's going to be our stack pointer, which we think of as the top of the stack. Well, when I started off with an empty stack, I said the top of the stack was right here. So I'm thinking of the stack pointer as where I am about to push to. So SP is the index for the next push. So my init function just says SP equals 0. And my stack, by the way, is just an array. So I initialize my stack by just setting SP equal to 0. If I want to push, well, SP says where my data should be stored. It's the index for the next push. So to push the number data, I'm just going to say stack bracket SP equals data. And then I need to increment SP to move the stack pointer, the top of the stack, to the next location. So I want to use SP first, and then I want to increment it. That's a post increment. So you can do it in 2 statements, you can do it in 1.
So, I was thinking like linked list wise, couldn't you just add to the beginning of the list?
Yep, yeah. Linked list is a little easier. With a list, yeah. But we're never popping, so it's more coincidental. But yeah, that would be how we would implement it with a list. Okay, so how do we pop from an array? Okay, so we're going to look up an element in the stack. So if we push a 10, 10 comes down here, SP is going to be equal to 1. If we want to pop this 10 off. So we need to subtract 1 from the stack pointer first. Because stack pointer is telling us where the first empty spot is. That's where we're going to push. So if we want to pop, we want to decrement the stack pointer and then read what's at that decremented location. So this is a post increment for push and a pre-decrement for pop. So when is the stack empty? What's the value of SP if there's nothing on the stack? Right, that's just 0. That's what we initialized it to. When is it full? Yeah, so in this case it's full if the stack pointer is 10. If the stack pointer is 9, that says the next push is going to go right here at index 9. That's totally fine. That's an available location. After we do that push, we'll increment the stack pointer to 10. That's when we know the stack's completely full. 10 is also the number of things that we're allowed to have in the stack. So if we allocate the stack with n locations of memory, when the stack pointer equals n, we can say the stack's now full. So we could modify our push. Before we push, we could say if the stack's full, throw an error. And if we pop, first we check to see if the stack's empty, and if it is, we throw an underflow error. Yeah?
So that reminds me, with strings, it stops reading the end of the character array when it hits a null pointer. How does it stop reading when it's an int array or a pointer array?
It doesn't. There's nothing to tell you hit the end of the array. This is where seg faults come from. You can just keep reading more and more and more. So we need to have something in here which knows, for example, that when SP equals 10, that's the end of the memory we allocated for this array. Otherwise, there's generally nothing we could put in here to signal the end of the array like we do with a string. Now with strings, ASCII code 0 is a null. It doesn't print as anything. Strings historically were used to store things that you would look at, say on a display or a printer, printable characters, so usually ASCII code starting with 32 going up to 126. So ASCII code 0, almost never would you want that to be a part of a string, so we can use that as a special value. Say if you're reading an array of characters and you get to a 0, that's not part of the string, that's the end. For an array of integers, we can't do that, unless there's some integer we know you're never going to use. So if these are temperature readings in Celsius, right, we could do -300 because we know you can never have -300 because it's below absolute 0. If they're test scores, we could use -1 because you never get a -1 on a test score. But in general, if it's just integers or floats or something like that, there's no value we can put in there to mark the end of the array. That's a C kind of issue. So we usually have to have something that tells us how big this thing is. All right, well, this is one way to implement a stack using an array, but there are other ways. For example, I could think of my SP as the index for the next pop instead of the index for the next push. So I want to initialize my stack pointer to -1. So that when I push, well, so when I pop, SP is the location for the next pop. So I want to return the value stored at the index given by SP, but after I do that, I want to decrement my stack pointer. So our pop goes from a pre-decrement to a post-decrement. And if you work through the logic, our push is going to say stack bracket plus plus SP equals data. It becomes a pre-increment for a push. Why? Because since SP is always the last thing that we're going to pop, the first thing we're going to pop, that's pointing to a piece of data on our stack. If we want to push something, we have to increment that stack pointer first to get to a new location. So we do increment SP and then we use that.
If you ran those side by side for a million different push pops, would there be any performance difference?
I suspect so, because 0 is always faster. But I don't know which one would be faster. But you could benchmark it. You could make a fixed but random driver that does a million pushes and pops in different ways and time them out. It would be interesting. All right, so your stack is empty when SP equals -1. Your stack is full in this case when SP equals 9. It means that the thing that you're about to pop is in the last location. Okay, so it's a parallel structure to the code, but the details change, right? But it doesn't upset us. So post increment, pre-decrement, pre-increment, post-decrement. Okay. Both of these assume that we start from index 0 in our stack, that's the first place we're going to write. Another possibility is that we could start by putting our first piece of data down here at the bottom of this array. Well, it's only the bottom because this is the way I drew it. It could be the top. But we could start off by putting it here, and then our push would be a decrement and our pop would be an increment. And we could do post-decrement or pre-decrement, and we could do pre-increment or post-increment for the pop. So there's at least 4 different ways we can do this. This is the way I usually do stacks when I'm coding up a stack myself. This is the way the PIC processor does stacks. Right? I think the stack pointer register tells you where to pop from. Instead of -1, it's 0, and then 0 doesn't actually exist on the stack. It's just PIC. Different ways to do this. Stacks are always implemented in hardware, so most processors have a hardware stack, but a lot of systems make their own stack. So the stack that we're using when we're running our code is, it's implemented by the operating system, but it's sort of using the hardware. But it can sort of be set up where we want. We can increment, decrement, things like that. But when you call the hardware itself, the CPU does certain things to, in the case of an x86, to the SP register. Right? It will decrement it and push things on there and so on and so forth. On the ARM processor, you can control which of these 4 schemes gets used by the hardware stack for your post increment or decrement. There's a pair of configuration bits on some ARMs, and you can say I want to use post decrement.
Again, is that only for the performance gain?
I don't know what the reasons are for that. I suspect if you're working on a particular system that wants to use post increment, it saves you from having to do a lot of extra code to adjust to what the hardware happens to do. I don't know how big a factor the performance business is, but the direction is pretty critical. Because on a lot of systems, right, your memory, if you look at the whole memory of the computer, programs usually start, well, they used to start at location 0. We reserve locations around 0 as reserved in Unix so that we can use null as a flag. It's never a good memory location. And if you forget to initialize something, you're guaranteed a seg fault because you'll try to access 0. But we usually start our program somewhere up here at the lower memory addresses. And our stack usually begins at the other end of memory. And we grow from, low addresses to higher for our programs. The stack grows from this highest location to smaller addresses. So your pushes are decrementing the stack pointer. And why is that? Because we don't know ahead of time how much memory you have. So when your memory is set up based on your hardware and the operating system and so on and so forth, the stack can basically just keep growing and growing and growing until it hits a memory boundary that it's not allowed to exceed. And then you get a seg fault, stack overflow. But if you look at these stack addresses, right, that's 7 with a bunch of Fs. That's a memory location that's about as high as you can get, right? It's a bunch of 1s and then an E550, right? That's the high end of your memory address space, and it decrements as you go up until you run out of memory. All right, the other way you can implement a stack is with a linked list, as we've already talked about a few times. Basically, insert at the beginning of a list when you want to push, remove from the beginning of a list when you want to pop. It's very easy, right? An empty list means there's nothing on the stack. So if the sentinel is pointing to null, your list is empty, and you can't pop. Otherwise, pop is just remove the node that's at the beginning of the list, so delete that, return the data value. And push is just insert a new node at the beginning of the list. So that's what you're doing with your license plates. When you add to your hash tables list, just insert in the beginning. And if you're using a list, when is your stack full? Yeah, when you try to create a new node to insert and you can't get any more memory from malloc, basically when you're out of memory. So this kind of stack, right? You declare it with a certain number of spaces, and you say, when I try to go past that, my stack's full. With a linked list stack, you can just keep adding and adding and adding until you run out of memory. Right, so that's more general purpose. All right, let me just mention in the last 30 seconds, the other thing we do with stacks and computers is we use them to store local variables. Right? When you run a function and you have a variable I inside your function, that's different from the I in your main program. It's different from the I in another function that you might call. And if your function calls itself, it gets a new local copy of the variable I. And it can change that, and the variable I in whatever called that is unaffected. Right? Where do all these local variables get stored? It turns out they get stored on the stack. And they don't get pushed and popped, but you back the stack pointer up a certain amount, and you say, okay, these locations are for my local variables. And when you say return, your stack pointer jumps back to where it was, right? And now all that memory that you use to store your local I, J, and K, that's available for other things to use. Either to store return addresses or store their own local variables. So sometimes we go through that in 270, sometimes not. But we'll look at that more when we start recursing. All right, exam tomorrow. Do not miss your midterm. If you have friends in here, tell them not to miss the midterm, please. Monday, we'll probably go over the midterm. Tuesday, we'll start talking about queues, another type of data structure similar to stacks. All right, I will see you tomorrow.